Okay, let's talk about the silicates, which are one of the main compounds that make up our soils and a lot of the rocks around us in the world. They also make up stuff like sand and clay and lots of other materials that I guess are all components of soils. Okay, so silicon dioxide, silicates and aluminosilicates are important components of rocks and soils. All of these compounds are based on the SiO4 tetrahedral. So we have a silicon in the middle surrounded by a tetrahedral shape of 4 oxygens. And what happens in all these compounds is lots and lots of these tetrahedra join together. And if we get a very blocky structure with lots of sharing through all of the oxygen atoms, we get a really hard mineral like quartz, which is what makes up sand. That has the formula SiO2, so silicon dioxide. But if we have different arrangements of this sharing, so if we have these sort of in sheets, like this structure that's sort of shown here, we get things that tend to be like form sheets like mica, so they flake away, really flaky minerals. They also form things like clay and lots of other things. Like I said, the quartz tends to form into stuff like sand. So you've got these tetrahedral with a silicon, so each of these blue tetrahedral would be a silicon in the middle of, and these red dots show all those 4 oxygen like that surround it, and they can join together in various structures. The other structure, you can get these sort of 3-dimensional porous structures, which are the zeolites that we looked at when we were looking at the water topic as well. You don't need to remember all the detail of this, but just that they all form from these joining together lots. The other important thing about these minerals is they all tend to have negatively charged surfaces. They all have oxygens all around the outside, and those oxygens tend to be carrying a negative charge. If we think about this, and you can get asked about stuff like this in terms of oxidation number, the silicon has an oxidation number of +4, oxygen has an oxidation number of -2. So if we go +4 plus 4 times -2, we get -4. So in a sense, each of these SiO4 tetrahedral, if you like, almost has a 4- charge. Obviously, if they share together, they don't. Every single one has a 4- charge because those electrons get used in sharing, so they're not sort of spare electrons. But generally, the surface of these will be very negatively charged. That has implications, as we've already talked about with zeolites, for soil nutrients. Not soil nutrients, for sodium and calcium ions to be absorbed in making water softeners. Go back to that. Go back and look at the water topic on water softeners if you can't remember that. But when these things are present in the soil, it is also really important for how the nutrients are absorbed to those soils and then how they are released so they can get taken up by plants. So inside of these tetrahedra, if you like, sometimes some of the silicon can get replaced by aluminium, and that's where the aluminosilicates come through. So in some cases, it's always a silicon in the middle. In other cases, sometimes an aluminium replaces one of the silicates, and that's how we get the aluminosilicates. So now let's look at write the formula of the anion given the formula of the silicate or aluminosilicate. So we've got the phlogopite here, and this is the formula for phlogopite. And what we need to firstly do is identify the aluminosilicate part of it, which is this part here. So basically, it's like a repeating unit in a polymer. That is the aluminosilicate part. So you can normally easily tell that from the formula. Now the next thing you need to be able to do though is work out what is the charge. So what charge is going to go here? Actually, I might use that. What charge is there going to be here on that aluminosilicate ion. And there's actually two methods that you can do to do that. We can firstly look at the counter ions to the aluminosilicate ion. So we have got, in terms of the counter ions, we've got a potassium, which would be +1. We've got magnesium. Actually, we're doing charge here, so I should actually write those not with the plus first. I should write, just plus, 2 plus. And obviously we've got 3 of those, so that's going to be 2 plus times 3. And then we've got hydroxide over here, which has a minus, and we've got 2 of those. So if we look at it in terms of charge, we can go, well, the amount of other charge in that ion is, there's a 1 plus, 2 plus times 3 is another 6, so we've got plus 6 to give us 7, and then we've got minus 2 times 1, so we've got minus 2, so that would give us a 5 minus charge. Correction, 5 plus charge. Why am I saying 5 minus? Well, if that is a total of 5 plus and all over it's neutral, then the aluminosilicate must have a charge of 5 minus. So we work out the charge of all the other things, and then the aluminosilicate must have equal and opposite charge. The other way to do it is, which is what I just did over here, is use oxidation number. So that the oxidation number of aluminium is +3, silicon is +4, oxygen is -2. So if we do this with the oxidation number method, we have +3 plus 3 times +4, so that's plus 3 fours are 12, minus 10 times -2, which is -20, and overall that is equal to 15 minus 20, which is equal to -5. Therefore, if the oxidation number of that overall ion is -5, therefore the charge will also be equal to 5 minus. So there's two different methods. They should give you the same answer. You can actually do both to check if you need to work out the formula for an aluminosilicate ion. That probably the only other thing I'll quickly mention too, I guess, is that where you have aluminium being replacing silicon in this lattice, so here this would normally be Si4010, and basically one of the silicons has been replaced by an aluminium. That increases the amount of charge, because if we had 4 silicons here, that'd be 16 minus 20, which would be -4, so we'd only have a -4 charge on Si4010. So in a sense, having an aluminium makes it even more negatively charged, makes the surface more negatively charged, therefore will even attract more positive ions to the surface. So now let's look at the exchange of cations, which are often our plant nutrients, at the surface of these negatively charged silicates or aluminosilicates. So we know that rainwater is slightly acidic. We talked about that earlier in the year, and we talked about that in year 11 because of the dissolved carbon dioxide, and then things like sulfur emissions and nitrogen emissions can even make it more acidic. Just in terms of terminology, we're going to use this thing here in bracket add for something that is absorbed to the silicate surface. So you're familiar with solid, liquid, gas, and then aqueous for something that's dissolved in water. Well, add in this case means absorbed to the silicate surface. So if we have something like potassium, which can attach itself to silicates, like this one up here, when that attaches itself, that potassium is potentially a valuable plant nutrient. When the rain falls, it contains some aqueous hydrogen ions because it's slightly acidic and has the presence of hydrogen ions. And what we do is we get exchange at the surface. So the hydrogen ions adsorb onto the surface and they release the potassium ions. those potassium ions released to water to be absorbed by the plant roots. Plants can get their nutrient, all good, plant grows, all healthy. However, if our rain is too acidic, what will happen is this reaction will get pushed too far this way, and all the potassium will get released. We won't have any left absorbed to be slowly absorbed over time, and this will tend to just leach down into the groundwater. Like it won't all, the plant can only take up a certain amount in a certain time. If it all gets leached out, then it will just basically fall down into the groundwater or wash off, and it won't be available to the plant in the future. A similar thing can happen if we have salt water, so saline salt water. If we've got absorbed potassium, we put salt water onto our plant, the salt gets absorbed, the potassium gets released. Initially, if it's a small amount, that might be okay because it might help the plant access that potassium. But if it gets a lot of salt all at once, all that nutrient basically just dissolves away. The plant can only take up a little bit, and the rest will just basically fall down into the water layer or run off, and that nutrient will be lost to the soil. So that's it for the soils topic, and particularly part B, which is the silicates, which we're focused on here. When you look at the book has far too much detail on this stuff. So if you're looking at the Essentials workbook, don't get stuck in all the detail there. They've got a heap of stuff that used to be in the course, I reckon still in the book, that is not in the course anymore. So don't get too put off by the level of detail in the book. What's here on this slide in terms of silicates and soils is what I believe all you need to know according to the SACE curriculum outline. Thank you.